So this is a video on the angle addition postulate, and our goal for this lesson is to introduce ourselves to angles and to be able to name angles and ultimately use the angle addition postulate to find the measures of angles. So before we get to angles, we have to first talk about rays. And rays are very similar to lines in line segments, but obviously are a little bit different. So what is a ray? A ray is a part of a line with exactly one endpoint, and it extends indefinitely in one direction. So if we think about this, we've already learned lines which go out in both directions indefinitely, and we learned about segments where segments are a part of a line but have two endpoints, right? It is a finite length. Well, a ray is kind of a combination of a line and a segment. It has one endpoint, but it still goes off towards infinity in the other direction. Now, just like we said, it's important to know how to name lines and segments. For example, we can say this is line AB or line BA with the specific line notation. Or we can say this is segment CD or segment DC with the specific segment notation. We have specific notation for rays. The way we name it is we take the endpoint, which in this case is M, and then we choose a point in the direction in which the ray is going, whether it's O or P, and we either write MP or MO with this ray notation. All right. One thing I want to emphasize is notice how the arrow is going towards P. Well, notice how this segment, or excuse me, this ray is going towards P. Okay, does that make sense for everybody? So, give you a quick non-example on how to not name it. How to not name. You would not say it is PM like so, right? Because P is not the end point, and it's not going in the direction of M. That would look something like this. Okay? So now that we know what rays are, it's also good to understand what are opposite rays. And the name really says it. They are two rays that go in opposite direction. So notice how we have JK, right? Rays JK starting at J going towards K. And ray JH, right? Starting at J going in H. But not only do they go in opposite directions, they also form a line L in this case. Okay, so just another vocabulary word to make sure that we understand what it means. So now that we know what rays are and opposite rays, we can finally dive into what are angles, because angles are formed by two non-collinear rays, right, not on the same line, that have a common endpoint. So notice how if I look at this angle, we're really dealing with two separate rays. We have BA and BC, but notice how they have the same endpoint B. Now, with this angle, and I see I made a little typo here, the two rays that make up this angle are called the sides, so BA and BC are the two sides. And we can also say that the point of intersection of the two rays is called the vertex. So just again, more vocabulary to be aware of. Now, naming angles, just like naming points, lines, planes, segments, and rays, can provide some challenges, but really are pretty straightforward. With angles, there's three different ways, we'll say three different ways you can name them. The first is by naming it as the vertex. So angle B, right? Angle B, B is the vertex, so we say angle B. Notice this angle notation in front of it. We can also call it by the points that outline the angle. And honestly, this is probably going to be the most commonly used one. But essentially, if I look at angle ABC, notice how if I trace those points, A, B, C, I'm tracing out the angle. I can also go CBA, which is in the reverse direction. Notice, though, I cannot call it angle BAC, right? Because think about it. Outlining it, tracing it, if I trace BAC, starting at B, going to A, and going to C, I would get this angle, B to A to C. And that red angle is not what we're looking for. So again, when you do this, name it this way, I should say, make sure you trace it out with your pencil or with your finger. Now lastly, you could also name it by a number. Not all diagrams will have numbers involved, but if it does, this is probably one of the easier ways to name an angle. Special note though, this is not the angle's measure. Okay, so if you see angles like 1, 2, 3, so on and so forth, that's just providing a way to label them. Typically with an angle measure, you'll see a degree notation, and we'll talk about that in the upcoming slides. So first things first, let's take a look at a couple examples. In this first one, part A, we want to name all the angles that have B as their vertex. So looking here, here is the vertex B, the point B, and we see that we have angle 1 and angle 2 having a vertex of B. Just so we're clear, even though 5 is right by B, if you were to trace out angle 5, you would see that 5, the vertex is actually C. Next, name the sides of angle 3. Well, angle 3 is right here. All right, so we see that we have the two sides, which are the two rays. So we have CE, ray CE, but we also have CB as the other side. Now, just to be clear, you can also call this CA, right? Because again, starting at the point, starting at the end point, going in the direction of the infinitely long line, we're going in, going in the direction of B is the same thing as saying going in the direction of A. So CA can be used as well. All right. Lastly, another name for angle GHL. So GHL is here. We can say it is angle H based on its vertex. We can call it angle 7 since there is a number involved on the diagram, or we can just call it angle LHG. We could trace it the opposite direction. Now, similar to segments having a specific length, or a finite length we should say, angles have a finite measure. And we measure these angles in units called degrees, and it's essentially derived by dividing the distance around a circle into 360 parts. So if you ever think about, a circle being 360 degrees, when you look at a protractor, think that a protractor is half a circle, and that is where we get all of these units. Now, be careful with the notation. When dealing with the physical angle, that means just the angle on the diagram, we use this angle notation out front, so angle DEF. However, when we want the measure, that means the actual numeric value, right? So we want some number to go with it. We put this little m out front that signals the measure. So finally, all of this leads us to really the important topic of today, which is the angle addition postulate. So it's very similar to the segment addition postulate, which, if you remember, says if we have a point B in between A and C, then we can say AB plus BC equals AC, right? This is the segment addition postulate. Why is it called segment addition? Because we are adding segment lengths. Well, with angle addition, it is very similar. The only difference is now we are adding angles. So here, and it might be a little bit harder to see because, segments are pretty straightforward, but angles could be a little trickier. Here we have really three separate angles. We have ADB, the red one. We have angle BDC, the blue one. And we have angle ADC, the entire segment. Well, if we cut the entire segment ADC up into these two smaller parts, we know that if we add the two smaller angles together, the measure of ADB plus the measure of angle BDC, we would get the entire angle, the measure of angle ADC. Okay? So we're going to just really finish up this video lesson working with a couple examples that use this angle addition postulate. So in this first one, we're given that YMC has a measure of 170 degrees. So YMC is this entire angle. We are given an expression for YMA, and we know that the measure of YMA added to the measure of angle AMC, which again we're given another expression for, is equal to the entire angle, which is YMC, right? Two smaller angles added together equals the whole thing. So substituting these values, we have our 5x plus 19 plus 5x plus 1 equals 170. Here we can solve for x. So 10x is equal to 150, and thus x is 15. Now in this case, it wants us to solve for AMC, which I highlighted as my green angle. So here we have 5 times 15 plus 1. 5 times 15 is 75 plus 1, so we get 76. Even though it's not asking for it, we can check our work by finding the angle of YMA. So 5 times 15 plus 19 is 75 plus 19. 75 plus 19 is equal to 94. And this should make sense because 94 plus 76 gets us a total of 170 degrees. Let's take a look at another one. So here we have ROS, which is 4x minus 20. We have SOT, which is the 3x plus the 14. And it tells us that ROT, which is the entire angle, is equal to 155. Well, the angle addition postulate gets us the equation. We're now going to use algebra to solve for the angle measures. So we have 7x minus 6 equals 155. Adding the 6 to both sides, we get 7x is 161. And dividing both sides by 7, we get, 23. X is 23. Here it wants ROS and TOS. So let's first get ROS. So we have 4 times 23 minus 20. 4 times 23 is 92 minus 20. So we get a angle measure of 72 degrees. For SOT, we have 3 times 23 plus 14. 3 times 23 is 69. So 69 plus 14, and we get 83. All right. Again, hopefully this makes sense, because when we add up the 72 and the 83, we get the entire measure of 155. Now I'm going to do one more example, very similar, but if you feel comfortable and confident, you could jump right to the video lesson quiz, and you can take that now. If not, I will go over one more with you. So in this case, we have ABC being 4x plus 2. We have CBD being 3x minus 7. And the entire angle, ABD, being equal to 100. Solving for x, we have 7x minus 5 equals 100. So 7x equals 105. So x is equal to 15. For ABC, we have 4 times 15 plus 2, which is 60 plus 2. So we get an angle measure of 62. For CBD, we have 3 times 15 minus 7. So we have 45 minus 7, which gets us 38. And again, 62 plus 38 is the entire measure of 100.